So yesterday, or Monday, we were in the middle of example 9 when we stopped at the end of class. Okay, this is where we ended on Monday. So we were trying to find all four zeros, right, to the polynomial, this fourth degree polynomial equal to 0. What are the four zeros? Right, four values of x that make this fourth degree polynomial equal to 0. And we had come down to this point right here where x squared minus 2x plus 5 is a factor. And so this fourth degree polynomial is equal to x squared minus 2x plus 5 times an unknown quotient, which is going to also be a quadratic, right? This is the fourth degree polynomial. This factor is a quadratic, so q of x is going to be quadratic. So to find q of x, we got to divide the fourth degree polynomial by x squared minus 2x plus 5 using long division. Okay? And that's where we stopped. And I said, you try to figure out what the quotient q of x is. Is there anybody who did attempted the long division? One, right? So several of you. Okay. What'd you get?
I got x squared plus 4x plus 1.
Oh, you're close. X squared plus 4x plus 1?
Yeah.
Either you're right or I'm wrong. Either you're right or either you're wrong or I'm wrong.
I got x squared minus 4x.
That's what I got. I got minus 4x. So let's do the long division together. And then, because back in, when we did long division, what was it, in 3.2, we didn't actually divide by a trinomial, right? We divided by a binomial, but not a trinomial. So, you know the procedure, right? The dividend has to be written in descending powers of x. And the divisor has to be written in descending powers of x. So, first question, how many times does x squared go into x to the fourth? Well, x squared goes into x to the fourth x squared times. So x squared is part of the quotient. And now you got to multiply this quadratic times x squared. So x squared times x squared is x to the fourth. Minus 2x times x squared is minus 2x cubed. Plus 5 times x squared is 5x squared.
Wait, can you do that again?
The multiplication, x squared times x squared is x to the fourth. Minus 2x times x squared is minus 2x cubed. And 5 times x squared is 5x squared. Okay? Sort of this, you're distributing, when you do the multiplication, right, you're distributing x squared inside the parentheses of x squared minus 2x plus 5. Okay? It's basically what you're doing. Okay? And so now you got to subtract that from the dividend. So I encourage you to put, whenever you do subtraction, put what you're subtracting in parentheses, or you won't distribute the minus sign correctly. So x to the fourth minus x to the fourth is 0. Minus 6x cubed plus 2x cubed is minus 4x cubed. 14x squared minus 5x squared is 9x squared. And then we bring down the minus 22x plus 5. Okay. So now you got to ask yourself, how many times does x squared go into minus 4x cubed? minus 4x times, right? You just use the rules of exponents. So minus 4x goes up here in the quotient. And now you got to multiply minus 4x times the divisor. And again, all you're doing is distributing the minus 4x inside parentheses. Minus 4x times x squared is minus 4x cubed. Minus 4x times minus 2x is 8x squared. And minus 4x times plus 5 is minus 20x. So now you gotta subtract that.
Shouldn't that be 19x squared? Under the 14 plus 5, 14x squared plus 5.
14, you really gotta distribute the minus sign. So you distribute the minus sign, that becomes minus 5x squared.
Okay.
Right? Okay, remember to distribute the minus sign. Okay? So when you distribute the minus sign, the sign of each of the terms inside parentheses changes. And now we just subtract this from the line up above. And again, you gotta distribute the minus sign. It's gonna change the sign of each of the terms inside parentheses. So we have minus 4x cubed plus 4x cubed, which is 0. 9x squared minus 8x squared, which is just x squared. Minus 22x plus 20x is minus 2x. And then we bring down the plus 5. X squared goes into x squared once. 1 times x squared minus 2x plus 5 is equal to x squared minus 2x plus 5, which we subtract from up above and get 0 for a remainder. Is that surprising that we got 0 for a remainder? It's not surprising if x squared minus 2x plus 5 is a factor of this 4th degree polynomial, right? By the remainder theorem, if this is a factor of this 4th degree polynomial, when we divide this 4th degree polynomial by this factor, you better get 0 for a remainder, or something's wrong. You either made a math error, or this isn't a factor of this polynomial after all. Alright. So x squared minus 4x plus 1 is the quotient over here, q of x. So we can write the right-hand side here as x squared minus 2x plus 5 times x squared minus 4x plus 1. Okay. Now, we already, so to find the values of x that make the left-hand side equal to 0, we already know if we set x squared minus 2x plus 5 equal to 0, we're going to get x is equal to 1 plus 2i and 1 minus 2i, right? We were given x equals 1 plus 2i is 0 of this 4th degree polynomial. And so by the complex conjugate theorem, 1 minus 2i is also 0. And that's how, using that, is how we came up with x squared minus 2x plus 5 as a factor of this 4th degree polynomial, right, on Monday. So to find the remaining two solutions to that equation, we just got to set this quadratic x squared minus 4x plus 1 equal to 0, solve for x, and we'll get the last two solutions. So you know the procedure. A in this case is equal to 1, B is equal to -4, C is equal to 1. And now we apply the quadratic formula. X is equal to negative B, which is -4, plus or minus the square root of B squared, which is -4 squared, minus 4 times A, which is 1, times C, which is 1, over 2 times A, which is 1. Well, the determinant under the square root, well, negative of -4 is +4. And the determinant under the square root is equal to 12. And 2 times 1 in the denominator is 2.
Can you simplify the 12?
Say what?
Take the 4 out of the 12.
Yeah, we're gonna reduce the square root of 12. Square root of 12 12 is equal to 4 times 3. Square root of 4 is 2. So square root of 12 reduces to 2 times the square root of 3. Division does not undo addition and subtraction, right? So we got to divide the 4 by 2 and 2 root 3 by 2. So we have x is equal to 4 over 2 plus or minus 2 root 3 over 2. 4 over 2 is 2. And the 2's cancel in the second fraction. We're just left with root 3. So the two remaining solutions of our equation, the fourth degree polynomial, are irrational. These are irrational. 2 plus square root of 3 is an irrational number. So 2 plus the square root of 3 is an irrational number. And 2 minus square root of 3 is an irrational number. So you know that complex zeros come in pairs. It's also true with integer coefficients in our polynomial equations. Irrational solutions come in pairs, okay, involving square roots, right, when you use the quadratic formula. All right. So these are the remaining two solutions to our equation. So if we write them all out, we have x equals 2 plus the square root of 3, x equals 2 minus the square root of 3, x equals 1 plus 2i, and x equals 1 minus 2i are the four solutions to our equation. Any questions on that? Okay. So let's flip over to example 10, and you will have everything you need to successfully complete the homework. All right. Example 10. Verify that x equals 1/3 and x equals 3/2 are zeros of the polynomial function, f of x, which is equal to a fourth degree polynomial. Find all other zeros and give the complete factorization of f of x. So, it's a fourth degree polynomial, and we know two of the zeros, so there are two remaining zeros to find. So f of x is equal to 6x to the fourth minus 5x cubed minus 2x squared minus 8x plus 3. Alright, so f of 1/3, you just put in 1/3 in for x, right? So when you do that, you have 6 times 1/3 to the fourth minus 5 times 1/3 cubed minus 2 times 1/3 squared minus 8 times 1/3 plus 3. Now I'm not going to do, we're going to do order of operations, PEMDAS. But when I did that arithmetic, following order of operations, I got 0. You can verify that yourself. Okay. Exponents, then multiplication, then addition and subtraction. Okay. And then you evaluate function at x equals 3/2. Now, if you evaluate f of x at x equals 1/3 and you get something else besides 0, either you or I made a mistake. Okay. F of 3/2, right? To verify that x equals 3/2 is a 0, you put 3/2 in for x on the right hand side. So 6 times 3/2 to the fourth minus 5 times 3/2 cubed minus 2 times 3/2 squared minus 8 times 3/2 plus 3. And when I did that arithmetic, following the order of operations, I got 0. Okay. So once you do the arithmetic, you verify that x equals 1/3 is the 0 of this polynomial function, this fourth degree polynomial, and x equals 3/2 is the 0 of this polynomial function. Okay. So x minus 1/3 is a factor of this polynomial function, and x minus 3/2 is a factor, right, from the factors there, which we've said, used many times already in this pack. All right. So to find the remaining two roots, right, they're going to come from a quadratic, right? If x minus 1/3 and x minus 3/2 are factors, then f of x can be written as x minus 1/3 times x minus 3/2 times some quadratic. We got to find that quadratic. Okay. So the first thing we're going to do is divide this fourth degree polynomial by x minus 1/3. So let me make a note. X minus 1/3 and x minus 3/2 are factors by the factor theorem. Okay? So the first thing we're going to do is divide this fourth degree polynomial by x minus 1/3. Since this is a linear factor, we can use synthetic division. What's c in this case? 1/3. It's plus 1/3, not minus 1/3. So we put 1/3 in our box, and then write out the coefficients in descending powers of x. And the coefficients are 6, minus 5, minus 2, minus 8, and 3. So you know the procedure. Bring down the 6, multiply it by 1/3, you get 2. Put 2 in the next column. Add it to negative 5. You get negative 3. 1/3 times negative 3 is negative 1. Put it in the next column. Add it to negative 2. You get negative 3. 1/3 of negative 3 is negative 1 again. Add it to negative 8. You get negative 9. And 1/3 of negative 9 is minus 3. And you box the last number. 3 minus 3 is 0. Remainder is 0. We better get 0 for a remainder, or x minus 1/3 is not a factor, or we made a math error. So the quotient from our synthetic division, right? These are the coefficients of the quotient. 6, so start going from right to left. Minus 9 goes with x to the 0, which is 1. Minus 3 goes with x. This minus 3 goes with x squared. 6 goes with x cubed. So the quotient from this synthetic division is 6x cubed minus 3x squared minus 3x minus 9. So f of x can be written as the factor x minus 1/3 times that quotient. 6x cubed minus 3x squared minus 3x minus 9. Now because x equals 3/2 is a 0 of our polynomial function, that means if you put in 3/2 in for x inside parentheses here, that better equals 0, right? Because that contains the factor x minus 3/2. Okay? So 6 times 3/2 cubed minus 3 times 3/2 squared minus 3 times 3/2 minus 9 better equals 0, because this third degree polynomial contains the factor x minus 3/2, right? When we factor this third degree polynomial, right, one of the factors is going to be x minus 3/2. So we can divide this third degree polynomial by x minus 3/2. So we put minus 3/2 in the box. Oh, it's not minus 3/2, it's plus 3/2. Sorry, even I get confused. X minus 3/2 is a factor. 3/2 is 0. Then what are the coefficients for that third degree polynomial? 6 minus 3 minus 3 minus 9. We're dividing that third degree polynomial by x minus 3 halves. And now we did the synthetic division. Bring down the 6. You multiply it by 3 halves, you get 9. That goes in the next column. Minus 3 plus 9 is 6. And then 3 halves times 6 again is equal to 9. That goes in the next column. Minus 3 plus 9 is 6. Again, you multiply 6 times 3 halves and get 9. Minus 9 plus 9 is 0. And you box the last number. That's the remainder. Remainder is 0, just like we expected. So, 666. Everybody's favorite number, right? So, x to the 0 is equal to 1, right? So this first 6 goes with x to the 0, which is 1. The next one goes with x. Next goes with x squared. So the quotient from this synthetic division is 6x squared plus 6x plus 6. So over here, our fourth degree polynomial can be written as x minus 1/3 times x minus 3 halves times 6x squared plus 6x plus 6. Now in this, we're going to set this equal to 0 and solve for x. But is there a common factor in this quadratic? What's the common factor? 6, right? So we're going to write this as x minus 1/3 times x minus 3 halves. And then we factor out the 6. When we pull out the 6, we're left with x squared plus x plus 1. Okay? Does everybody see how I pulled out a 6? Because 6 is a common factor of those all three terms. Yes, sir.
Does it matter the order in which you divide those two steps?
No, it doesn't. Ogden brings up a very good point. Okay, we could have done 3 halves first, and then 1/3. It doesn't matter because they're both x minus 1/3 and x are both factors. Okay. Okay. All right. I just did it that way because that's the order in which the zeros were presented in the problem. So that, I guess that's the reason why I did it in that order. All right. So we can now set x squared plus x plus 1 equal to 0 and solve for x using the quadratic formula. Okay. So everything a is equal to 1, b is equal to 1, c is equal to 1. Okay. So by the quadratic formula, x is equal to negative b, which is negative 1, plus or minus the square root of b squared, which is 1 squared, minus 4 times a, which is 1, times c, which is 1. All divided by 2 times a, which is 2 times 1. So we have negative 1 plus or minus the square root. Well, when you simplify this, it's just going to be 1 minus 4, which is negative 3. So we have the square root of negative 3 over 2. Well, remember, division does not undo addition and subtraction, does it? So this is equal to minus 1/2. Actually, I'm gonna write it over here. This is equal, x is equal to minus 1/2 plus or minus the square root of -3 over 2. But square root of -3 is written as what? I times the square root of 3, right? Over 2. So the two zeros from this factor, x squared plus x plus 1, are x equals minus 1/2 plus the square root of 3 over 2i, and x equals minus 1/2 minus square root of 3 over 2i are the last two zeros. Okay. Right? The first two are x equals 1/3 and x equals 3/2, and the last two are x equals minus 1/2 plus square root of 3 over 2i, and x equals minus 1/2 minus square root of 3 over 2i. Okay. Well, we got to write out the complete factorization, right? So we got to write this out. This quadratic out is a product of two factors. So f of x is equal to, I might cut in this, well, this, I'm gonna, f of x is equal to, I'm gonna pull this 6 out front, that's our leading coefficient, times x minus 1/3, times x minus 3/2. And now, the factors, right, these are the zeros. So to get the factors, right, I gotta add 1/2 and subtract square root of 3 over 2i to get the factors. So I have x, the first factor. So I have x plus 1/2 minus square root of 3 over 2i. And then second factor, gotta add 1/2 and add square root of 3 over 2i to both sides to get the second factor. X plus 1/2 plus square root of 3 over 2i. This is the complete factorization of our fourth degree polynomial. Okay. Any questions on that? All right, so now you got everything you need to successfully complete the My Math Lab, the WebAssign homework. Okay. Hey, is there anybody who didn't get the 3.3 handout, which we just finished? Come on down if you need a hard copy.
Oh, I'm good.
You're good?
Yeah, I'm good.
Good. All right, so let's move on to 3.4. gamma. All right. So we have been finding the zeros of polynomial functions. And some of them have been complex numbers, and some of them have been real numbers. We're going to take things a little bit further in this section. So you might want to write this at the top of page 1 above the heading that I'm about to put on the board. This is our introduction to this section. Okay. So the zeros of polynomial functions up to this point have been complex, right? They're either complex numbers. Right, complex numbers are of the form a plus bi, right, where a and b are real numbers and I is the imaginary number, square root of -1. And they've been real numbers. Okay. Now, the zeros that are real numbers can be broken down into 2 groups. They can be rational numbers, what are called rational numbers, or they can be irrational numbers. You know, the numbers on the real number line can be broken down in 2 groups, rational numbers and irrational. Does anybody know what makes a rational number rational?
It can be written as a fraction.
It can be written as a fraction. But more specifically, it can be written with a fraction with an integer and a numerator and an integer and a denominator, right? I mean, technically speaking, square root of 3 over 2 is a fraction, but square root of 3 is an irrational number, right? So she's correct. Right? Rational numbers can be written as a fraction, but they're written with an integer in the numerator and an integer in the denominator. Okay? So examples of irrational numbers, right, are square root of 2, square root of 3. These numbers cannot be written as a fraction. Okay? When you write out their in decimal form, right? There's no repeating pattern in the decimal. Okay? With rational numbers, there's a repeating pattern. Okay? There can be a repeating pattern. So, a rational number, as she pointed out, is a fraction, but more specifically, it's a fraction of the form p over q, where p and q are integers. So examples of rational numbers are 1/2 minus 3/4, 0.3, even though it's not written as a fraction, is a rational number, because it's equal to 3/10, which is a fraction. Okay. And whole numbers are rational numbers because the number 4 can be written as 4 divided by 1. Okay. So that's what rational numbers look like. And this section 3.4 has to deal with finding the zeros of polynomial functions, okay, where some of those zeros may be rational numbers, okay? And that's what we're going to be dealing with in this section, starting tomorrow, okay? So have a good day. Don't forget, we have a quiz tomorrow over section 3.2, okay? And we'll cover this 3.4 tomorrow, okay?